Now that I have the notion of potential energy, I should probably look around for other kinds of conservative forces for which I calculate the potential energy. It's just such a thing that I'm going to do today. It turns out it's a very limited set of forces for which we'll find potential energies in our physics. There are many, many potential energies in the full width and breadth of physics research, but we need only concern ourselves with a small subset. I've already calculated the gravitational potential energy, demonstrated that it's an energy that is not time dependent, that since the gravitational, this is the criterion for conservative forces, that the force not be time dependent, only be position dependent, and that the work done by that force is independent of path, that it doesn't matter which way you go to get from point 1 to point 2, that the amount of work done is the same. And we found that the force of gravity has that property, and based on the very, very fundamental definition in physics that the work done is equal to the negative of the change in the potential energy, I was able to derive the gravitational potential energy. Well, today what I'd like to do is derive another potential energy, and that is the potential energy of a spring. Earlier on, we were talking about Newton's laws. I introduced a list of forces that I could potentially see in problems, and one of the forces on that list was the spring force. And I said that there's an equation for how much force you get from a spring, but I didn't exactly write the expression for it. But I knew that it would be coming later. Well, here it is. So for a moment, let me describe this spring force, and then once I have a good description, I understand the behavior of the spring force, then I can just go ahead and apply this definition for the change in potential energy and derive the spring potential energy. It should not take me long at all. Imagine that I have here some sort of fixed barrier, like a wall, and attached to it I have a spring. And I'll draw my spring like this. It looks a bit like a resistor, but there it is. And I have a mass on the end of the spring. And what I want to do is investigate the spring force. Now, I've drawn the spring here in a very common fashion as a coiled bit of wire that has an elastic property. When I stretch it from its unstretched length, its tendency is to draw itself back to its unstretched length again. And if there's some distance between the coils, if I compress it from its unstretched length to a compressed position, then it will exert a force to expand itself to the unstretched length again. So it can compress or stretch, and it always exerts a force that opposes the stretch or the compression. In this way, we say that the spring is a restorative force. A coiled bit of metal, by the way, is not the only kind of spring or spring-like behavior. Imagine I simply have a metal rod and I pull it down from its straight, like I fix it at one end, and I pull it down, I let it go, and it springs back to its original position. So this general description I'm doing has great utility because it applies not only to this, but to pretty much to all elastic behavior. And as our physics goes on, I'll explain more and more what the limitations of that are. But what I want to do is I want to investigate the behavior of this spring. And in doing so, I want to come up with a law that tells me how much force a spring will exert based on the amount of stretch or compression that I apply to the spring. So the first thing that I do is I draw a picture of the physical situation so I understand the mass here that I've attached just for my convenience and my understanding. If I just leave the end hanging, I'm not sure what that means. So I have this mass here and I can pull on it. And if I pull on it, it will be directed, pulled to the right here. It'll stretch the spring to the right, but immediately we know from experience, I'll feel the spring pulling back to the left. And if I take it here in its rest position and push it to the left, I'll feel the spring pushing to the right. You'll recall a thing that I did with friction was that I drew a free body diagram and said, I may not know, or I may not have any way of directly measuring how much spring force there is, but I can apply my own force that I call F applied, that I'm showing here directed to the right, and that there's a force in this direction directed to the left, which is the spring force that I'd like to investigate. I can't directly, get in here and understand the fundamental nature of the spring force, but if I apply my force in equilibrium with the spring force, that is, the acceleration is equal to 0. If I set the acceleration equal to 0, a consequence of that is that these two forces would be equal to each other. And so I've devised an experiment by which I can determine what the spring force is for different values. And so what I'll do is I'll go in a laboratory and I'll set myself up a situation where I can apply some force, and then I'll make a graph of the force that I apply, which is equal to the spring force, so I'll just write Fs, as a function of how far I stretch or compress. I'm just telling you, it's a fact of the nature of the thing that I'm going to get the same behavior whether I stretch it or compress it. It doesn't matter. So I'm going to make this graph that describes this. Well, where do I start here on the x-axis? What I'm going to do is I'm going to set the rest position of the thing, which we call x0, the initial stretch. I'm going to set that equal to 0. So x0 is equal to 0. This is a very, very common practice when dealing with springs, to set the relaxed position, so-called unstretched position, as the 0 position. It is effectively the same thing as when I work with gravitational potential energy. I get to choose where the height is 0. Potential energy always has a reference associated with it because of this fundamental idea that the work done is equal to the change in potential energy. I can set the initial potential energy equal to 0, which you'll see I'll do. So then I'll stretch this thing over to here. I'll pull it over to the right using my applied force. And as I do, I'll get more and more force. And what I find on my graph is that I get basically linear behavior, approximately linear behavior. This is an important point. No spring is actually completely linear, right? It's just sort of approximately linear. Linear is a good approximation for the behavior of most springs. As long as I don't stretch them very far. Imagine I have a coiled bit of wire and I pull on it. I might get linear behavior of the force. If I pull harder and harder and harder, eventually I stretch it out so it's just a wire. And the amount of force that it exerts becomes quite large indeed, and then it snaps and all kinds of real-life practical things happen. When that happens, this line can go a bit crazy and start to curve upward and not have linear behavior at all. But as long as I'm very relaxed with the spring, I find experimentally that most springs have this sort of linear behavior. And so if I look at this graph, I see the relationship is going to be linear between the force that the spring force that I get and the stretch that I exert. I look for the slope of this so I can write that linear relationship. Well, along the x-axis I have delta x, the displacement, and along the y-axis I have the force that I get. I get the force that I get. And so that ratio to the force to the amount of stretch that I get we call K. K is the spring constant of the spring, sometimes called the stiffness constant. And it has units quite naturally, you see, as being the rise over the run. It's going to have units of newtons per meter. I'm confused as to why students find this difficult to recall the units of the spring constant. The spring constant tells me the number of newtons I get for every meter that I stretch or compress the spring. It tells me the number of newtons that I get for every meter that I stretch or compress the spring. That's very straightforward. So if I write this as a linear relationship, the force of the spring, whether it's stretch or compression, I would find I get the same experimental result, is K multiplied by the displacement delta x. But recall, I choose, quite arbitrarily, the unstretched length, x naught, to be equal to 0. So I can write this as K times x. Now what I've written here is not actually my spring law because it's a relationship among the magnitudes. It's a relationship among the magnitudes. I want to write this as a vector law because naturally the spring force is a vector. But it's very curious behavior that if I exert a force to the right, the spring force is to the left. When I exert my force to the right, the system displaces to the right. So the displacement is to the right, the force is to the left. If the displacement is to the left, the force is to the right. That is, the force is restorative and always opposite the direction of the displacement. So when I write this as a vector law, my final version of the spring force law, I'll write the spring force, and I'll put a harpoon on it to let you know that I'm talking about the vector version of the law, is equal to negative kx, where x is the vector displacement. So the negative sign that appears in the law, as I write it this way, that negative sign that appears in the law, is there sort of expressing my understanding that the force is always opposite the direction of the displacement. The force is always opposite the direction of the displacement. I treat this negative sign like it's conceptual and not mathematical. When I'm, as a practical matter, when I'm working with spring force, I don't worry about that negative sign in the law. I only worry about how many newtons of force am I getting in this situation. All right, so that negative sign you see is a sort of, I think of it as a conceptual negative sign. I'm certain that there are folks who disagree with me. Now that I've defined my spring force, I understand that it's linear, it's quite simple. I have to ask myself, is it a conservative force? And the answer to that on one of the criterion is absolutely yes. It depends only on position. It does not depend on time, it does not depend on velocity or any other physical quantity. It depends only on position, which is a requirement of a conservative force. The other requirement is its work independent of path? Is the work done by it independent of path? Well, that turns out that it's true. I need to calculate the amount of work done by the spring force in order to compute the spring potential energy. So by way of proving those two things at once, I'll just go ahead and do the very, very essential job of calculating the spring potential energy. So this we'll consider to be essential, this next bit that I'm going to do here, and we'll label it the spring potential energy. And so we know what the formula is here. We're going to start with this definition that the work done by a conservative force is equal to the negative of the change of the potential energy. So here, I'm going to calculate the work done, which our most general form of work is the F dot dr, which in this case is going to be the spring force, which is negative kx dotted into dx. I've taken the potentially three-dimensional work and I've made it a one-dimensional problem by simply casting it along the x-axis. Now, the displacement is along the x-axis, and the differential in this integral is along the x-axis. So there's no taking a component of the force in the direction of the displacement. It's already in the direction of the displacement. Not actually. It's opposite the direction of the displacement. But I've already taken care of that here with the negative sign that's in front of this. So when I do x dot dx, that's just x times dx. And in computing the work here, what I have is a negative sign out in front, the integral of kx. I could have taken the k out, I guess. Well, kx dx. Well, that's a simple integral to solve because the integral of x dx is simply x squared over 2. And so the result of this integral, I guess I'll put limits on the integration now, from the initial stretch to the final stretch, but recall I'm going to make that initial stretch equal to 0. But for the moment, I'll leave it in there as x naught, so I get the most general result that I can. So this is going to be negative k x squared divided by 2, that evaluated from x naught to x, so it's going to be negative 1/2 k x squared minus x naught squared. And I'm saying that that is equal to the work done, which is equal to the negative of the change of the potential energy. What the heck? I feel like it. X naught is equal to 0, so I'll set that. And so the work done, which is equal to the negative of the change in the potential energy, which is equal to the negative of the final potential energy minus the initial potential energy, is equal to 1/2 k x squared, where of course the initial potential energy I've set equal to 0 by choosing x naught equal to 0. And so I find, drop the negative sign, negative 1/2 kx squared, pardon me. And so the change in potential energy is just the potential energy, which I'll label the potential energy of a spring. The negative sign out front here cancels that negative sign, and what I find is that the spring potential energy is 1/2 k x squared. Notice that that spring potential energy depends only on the initial and final configuration of the system, and in no way depends on the path from beginning to end. It's true that I set x naught equal to 0, but ultimately the change in potential energy depends only on where you start and where you finish, and does not depend on the path anywhere along. So two things at once here. I have demonstrated that indeed the force exerted by a spring is a conservative force, and I have also derived the spring potential energy, which I now can use in solving problems. But in our next lecture, we're going to discover that this is all part of a greater concept that we're all already very familiar with, which is the law of conservation of energy.